This video, I'm going to be detailing Diffie-Hellman key exchange. Well, there's a common dilemma in cybersecurity. How do two people establish a secret password over a network where an eavesdropper, let's say her name is Eve, is logging every single packet? If you just send the password, Eve gets it. If you encrypt the password, how do you share the key to decrypt it? Well, this is what two smart people, Diffie and Hellman, solved during 1976. Let me give you a scenario where we have Bob and Alice. In this scenario, Bob and Alice are sharing a hypothetical color as a password in order to set up a secure connection via the internet. The first color that they share, yellow, is visible to everyone. As we can see in the diagram, Eve is able to see this public color that Bob and Alice are attempting to share. Here's where Diffie-Hellman comes in. Alice chooses a secret color, let's say blue, and Bob chooses a secret color, let's say it's red. They keep these colors hidden. Alice mixes yellow and blue, which is her secret color, to get a new visible color, which is green. Eve can still see this color green. She cannot, however, see her secret color blue. Bob mixes red with yellow to get a new visible color, let's say orange. They send their mixtures to each other over the public channel. Like I said earlier, Eve can see yellow, orange, and green, but she's unable to determine the exact mixture that led to these colors. Alice then takes Bob's orange and adds her secret blue. Bob takes Alice's green and adds his secret red. Both end up with the same final mixture, muddy brown. Eve is left stuck trying to separate the colors from previous. Let's move on to modular arithmetic. Let's take this example. We have 14 mod 12 equals to 2. This might look confusing at first, but let's use this clock as an example. Mod 12 means that we're starting at 12. 14 is the amount of paces that we move across the clock. So you would think that 14 mod 12 would be 26. However, after a full completion of a cycle, you then reset with 12 becoming 0, and then you add the remaining 2 to get your final answer of 2. So quick examples. What do you reckon 16 mod 12 would be? Well, it's 4. 5 mod 3? 2. Final one, what about 9 mod 3? 0. Because like I said earlier, once you complete a full cycle, it resets to 0. Moving on to the discrete logarithmic problem. Why this is a one-way street. If I tell you I started at a certain hour, added a bunch of hours, wrapped around the clock a few times, and landed on 2, can you guess my exact starting number? No. It could have been 1, 5, 9, etc. The wrapping process destroys the history of how you got there. This is what prevents an eavesdropper from reversing the math. The ingredients. So in Diffie-Hellman, we have a massive prime number usually, P, and we have a generator, G. For the purpose of simplification, I want you to think of a generator as something that creates randomness. It's a little bit more technical than that, however, that's the gist of it. And these two variables are public. Going back to Bob and Alice, they have secret values, lowercase b for Bob and lowercase a for Alice. Now, these two values that I'm about to reveal, Eve doesn't know what these values are. In fact, only Bob knows his value of 6 and only Alice knows her value of 4. These are the formulas below. For example, with Alice, her value, A, capital A, will be equal to G, the generator, to the power of her secret number, mod P, the public number that both Bob and Alice agree with. And it's the exact same for Bob. The only thing that's different is his secret is lowercase b. Let's use the values p is equal to 17 and g is equal to 3. Remember that these values are public. Eve can see these. Going on to the equation, Bob's becomes 3 to the power of 6 mod 17, which is equal to 15. And Alice's becomes 3 to the power of 4 mod 17, which is equal to 13. Eve is sniffing the network. She intercepts p is equal to 17, g is equal to 3, capital A is equal to 13, and capital B is equal to 15. However, to steal the secret, she has to solve 3 to the power of a mod 17 equals to 13. With tiny numbers, she can guess. With a 2048-bit prime, her computer will burn out before she finds it. Effectively, she has to brute force a massive number, which theoretically might be possible, but practically, without supercomputers, is not possible. Bob then sends his value of 15 over to Alice, as we can see highlighted in red, and Alice sends her value of 13 over to Bob. They then perform this new and final equation, and they both receive the final number 16. The reason they got the exact same number boils down to a high school exponent rule. X to the power of y to the power of z, which is the same as x to the power of y times z. Both generated the number 16 without ever sharing it. They can now use 16 as the password for an AES encrypted chat. In modern contexts, we now use perfect forward secrecy, PFS. Instead of using static keys, a brand new key pair is generated for every single session. If a server's master private key is stolen a year from now, past traffic remains completely unreadable. We also use elliptic curve Diffie-Hellman, ECDH. Standard Diffie-Hellman requires massive keys to stay secure, whereas ECDH achieves the same security with much smaller keys, saving massive amounts of compute and bandwidth. The flaw. Standard Diffie-Hellman does not provide authentication. Alice thinks she's exchanging keys with Bob, but she might actually be exchanging keys with Eve, who is simultaneously exchanging keys with Bob and vice versa. The fix. Diffie-Hellman must be paired with an authentication mechanism, like digital signatures or SSL/TLS certificates, which is exactly where RSA or ECDSA comes back into the picture to sign the DH parameters. I will very shortly be doing a video on RSA. If you want me to do other videos on these topics, please leave a comment. And that's the magic of Diffie-Hellman key exchange. It's a brilliant piece of mathematical choreography that allows two complete strangers to establish a bulletproof secret key of a completely compromised network without ever actually sharing the key itself. It's the unsung hero keeping your daily internet traffic secure. But remember, Diffie-Hellman only lets you agree on a secret. It doesn't actually prove who you're talking to. To solve that identity crisis, we need digital signatures and full asymmetric encryption. And for that, we have to look at RSA. If the clock math finally clicked for you today, hit that subscribe button, drop a comment below, and I'll see you in the next video where we break down RSA.